everyone. In this video we will be taking a look at energy, making use of the principle of conservation of energy particularly. A possible definition of energy is a measurement of an object's ability to do work. The standard unit of measurement of energy is in joules, which is the same as a combination of units of newtons times meters, as well as kilograms times meter squared over second squared. There are various different kinds of energy which can all be interchanged between each other. There is kinetic energy, which is the energy intrinsic to an object in motion. There is also gravitational potential energy, which can be thought of as how much energy the object has stored up by being lifted by some height. And the last type we'll be seeing in this class is spring potential energy, which can be thought of how much energy is stored up in a spring by being stretched or compressed. Now during this unit we also do run into work, which is the amount of energy a force puts into or takes out of a system. While the various forms of energy can trade between each other, the total amount of energy in a system is always conserved unless there is some external force that's doing some kind of work to the system. This is referred to as the conservation of energy, which in most general terms can be written as the sum of all initial energy plus any work done by an external force, besides gravity or a spring, must be equal to the sum of all final energies. I say work done by external forces besides gravity or a spring force because those are already accounted for in the potential energies. Similar to force problems, which depend on making sure you're accounting for all possible forces, energy problems often involve making sure you're accounting for all the different kinds of energies that are present in the problem. Let's take a look at this example where we have an object with a mass of 100 grams, falls from a height of 20 centimeters above a spring, landing on top of it and causing the spring to compress. If the spring has a spring constant of 200 newtons per meter, find the length that the spring compresses. When possible for these energy problems, we might want to start by drawing ourselves a diagram of the situation. Again, not unlike force problems. The difference here is that there will be both an initial and final moment to distinguish between. For our initial moment, we know the mass starts up here in the air, above a spring. We know this mass is equal to 100 grams, which if we convert is 0.1 kilograms. We know that it starts a distance of 20 centimeters above the spring when it's uncompressed. That 20 centimeters is again something we might want to convert, which would give us 0.2 meters. And we could go ahead and label that the spring has a spring constant of 200 newtons per meter. Then we could draw another diagram for our final moment in time. What has happened here? Well, the object has landed on the spring and made it compress. Keep in mind for this vertical diagram we're drawing, if the spring has been compressed, it has gone down some vertical distance, where our object has now landed on top of it. Since the spring has been vertically compressed, some distance, let's call x, that is an additional vertical distance x that the object that landed on the spring has traveled downwards. Other than the spring and gravity, which are already accounted for in potential energy, there are no external forces to worry about here, so the energies should be conserved without any work to worry about. So however much energy we have initially should equal however much energy we have in the final situation. Since our object here is changing height, we should definitely be including gravitational potential energy. Now that we realize that, we might want to clearly indicate where we are calling a height of 0, or where to call y equals 0. For some problems, such as ones where we measure from the ground, we have an obvious choice of what to call 0. In this problem, however, there are two standout options. We could call the starting equilibrium position of the spring as our y equals 0, or we could call where the spring ends up as y equals 0. Either choice can work as long as we're consistent. For this problem, I will be choosing our starting position of the spring as y equals 0. So I'll label this as y equals 0 right here. So anything above y equals 0 will be positive values, and anything below y equals 0 will be negative values. That lets me call my initial height of this object as the 20 centimeters, or 0.2 meters, since it is starting just that distance above y equals 0. Meanwhile, in the final diagram for my final height, I have gone down below y equals 0, so I'm now in the negative values. And if I've gone down by that value of x, my y final should be negative x. In this case, I'm treating x as a positive distance that this spring has compressed. So if I'm comparing to x distance down from y, that's why it gets a negative. In addition to the object falling, there is also a spring which is being compressed, so I should be including spring potential energy in my energy equation. Initially, the spring starts uncompressed, so the x initial equals 0. Meanwhile, the stretching or compressing of the spring in my final situation is that distance which I've called x. That leaves us with only one more energy to consider, of kinetic energy. Now, while there is motion happening between the initial and final moments of time, everything is at rest at the initial and final moments of interest. The falling object is implied to start with an initial velocity of 0, and in order to fully compress the spring, that means the object has now stopped moving in the final scenario. Otherwise, if it was still moving, it would still be compressing the spring further. So our initial and final velocities for our kinetic energies are both 0, which means we don't really have to consider kinetic energy. So going to our conservation of energy equation, we know we have to consider both types of potential energy, but not worry about kinetic energy. So on the left side, we should have potential energy due to gravity initial, plus potential energy due to a spring initial. Add those up and we should get potential energy of gravity final, plus potential energy of a spring final. Using our equations for potential energy, this should end up looking like mg times y initial, plus 1/2 times the spring constant times the initial stretching of the spring squared, equals mgy final plus 1/2 kx final squared. Now if we plug in all the numbers we know, mass is 0.1 kilograms, times gravity is 9.8 meters per second squared, times our initial height of 0.2 meters, plus 1/2 times our spring constant, which the problem gives us as 200, times the initially uncompressed spring, so 0 squared, equals mass 0.1 times gravity 9.8 times our final height. We went down a distance of x, so minus x from y equals 0, plus 1/2 times the 200 spring constant times the final amount the spring got compressed, which is x squared. Doing some of these calculations, we get 0.196 plus 0 equals negative 0.98x plus 100x squared. Moving things around, we see we get a quadratic. So 0 equals 100x squared minus 0.98x minus 0.196. Using either polysolve on our calculator or solving by hand with the quadratic formula will give us two mathematical solutions to this equation, which would be 0.049 as well as negative 0.0396. Since we defined x as a distance that the spring compressed, we are only interested in positive values for distance, so we will rule out the negative answer, meaning our value of x is the 0.049 meters, or about 5 centimeters, is how much this spring will be compressed by. Let's also take a quick look at a problem that involves work. An 80 kilogram person riding a sled has reached the bottom of a hill moving at a speed of 7 meters per second. If the coefficient of kinetic friction between the sled and the ground is 0.3, find how far the person will travel before they come to a stop. It is worth mentioning here that this problem could be done with a combination of net force equations and kinematics. But let's see what the energy approach looks like here. In this case, for our initial diagram, we know this person on a sled is moving across the ground, initially with a speed, v initial, equal to 7 meters per second. We know their mass is 80 kilograms. So if we wanted to draw all the forces acting on this person, there would be gravity, mg, going straight down, a normal force upwards, and since we know there is friction here, friction opposes motion, so it would be backwards. They will move some distance, which I'll call d, until our final situation, where the person has reached the end of their path, and therefore has stopped moving. They've traveled as far as they could, and friction has slowed them down to a stop. For this problem, friction is an external force, which we have to consider doing work. So when we go to make our conservation of energy equation, all of our energy is initial, plus any work done by friction, will add up to whatever our E final is. Out of all the energies we know about, which ones do we have to consider? Our object isn't changing heights, so we shouldn't have to worry about potential energy due to gravity, so no potential energy of gravity. There's no springs involved, so no potential energy of a spring. However, there are velocities here, there is motion, so yes, we should be considering kinetic energy. Also, when we think about work, whatever force is doing the work times the distance times the cosine of the angle between the force and displacement vectors. In this case, our displacement vector is moving to the right, while our force vector is going in the opposite direction. So these make a 180-degree angle that we should be considering as our theta. So plugging in to get our work, we get that work equals whatever the force of kinetic friction is times the distance times cosine of 180. But that just works out to negative Fk times distance. So if we now plug into our energy equation, the energy initial is just only going to be initial kinetic energy, so 1/2 mv initial squared, plus the work, which is minus Fk times the distance, which should be equal to our final energy, which, considering there's only kinetic to worry about, is 1/2 mv final squared. So we have the equation we want to solve here. What are we looking for? That is the d distance. We have mass to plug in, we have velocity initial and final to plug in, but we don't yet have this kinetic friction. So we have to go and think about how can we get that outside of this equation. Well, let's recall that the force of kinetic friction is given by the coefficient, which the problem does give us, of kinetic friction, times the normal force. The normal force isn't something that's directly given to us. However, if we go back and think about our net forces, since this object isn't moving up or down, the upwards and downward forces of gravity and normal force must be exactly canceling each other. So the normal force must equal mg. So our force of kinetic friction equals the coefficient of kinetic friction, which we know, times mass times gravity, which are all things we know. Plugging into our energy equation gives us mu sub k times mg, replacing our Fk. And now let's start plugging in numbers. So 1/2 times the mass of 80. Velocity initial we know is 7 squared, minus the coefficient of kinetic friction as 0.3 as the problem gave us, times the mass again of 80, gravity 9.8, times the distance d, which we are looking for, must equal 1/2 times the mass of 80, times the velocity final, which is just 0. We have come to a stop. Doing some of these calculations, we get 1,960 minus 235.2 times d equals 0. This tells us that 235.2d equals 1960. And divide both sides by 235.2 will give us a distance d of 8.33 meters, roughly. That concludes our brief look at energy. Though similar to force problems, might be a topic we want to get some extra practice with, as problems can be phrased or given to us in different ways.